Welcome, everyone. Today we are exploring the foundational environment of Azure Machine Learning. Let's get started. Welcome, everyone. Today we are focusing on one of the most critical foundational concepts in Azure Machine Learning, creating and managing a workspace. So, what exactly is an Azure Machine Learning workspace? Think of it as the ultimate command center for your entire machine learning lifecycle. It is the top-level resource in Azure that provides a centralized place to work with all the artifacts you create. When you are experimenting with data, tuning hyperparameters, or deploying models, everything happens within the context of this workspace. The basics are quite straightforward. It holds your compute targets, your data assets, your MFlow tracking experiments, and your registered models. Why is this so important? Because without a well-managed workspace, collaboration among data scientists and engineers becomes chaotic. We use it to organize our work, securely store credentials, and ensure that our experiments are reproducible. How do we start? We simply provision this resource in Azure, which automatically sets up a storage account, key vault, and container registry behind the scenes. This allows you to immediately jump into deep dive activities like running automated machine learning jobs or building custom pipelines without worrying about the underlying infrastructure. Let's take a look at this diagram to visualize the structure of an Azure Machine Learning workspace. At the very center, we have the workspace itself acting as the core hub. Radiating out from this hub, you can see the primary resources it manages. On the top left, we have data assets, which feed your training scripts. On the bottom left, compute targets, the actual virtual machines or clusters that do the heavy lifting of running your code. On the right side, we see experiments and MFlow tracking, which record your parameters and metrics so you never lose track of a model's performance. And finally, the models repository where your finalized, trained models are registered and versioned. As I walk you through these nodes, notice how the workspace acts as the protective boundary and organizational shell for all these moving parts. It is not just a folder, it is an active management layer. By keeping all these resources tightly integrated, the workspace ensures that when you run a pipeline, your compute instantly knows where to pull the data from and exactly where to save the resulting model. It simplifies the entire workflow. Now that we know what a workspace is, why do we need more than one? This brings us to the core of machine learning operations, or MLOps. In a professional setting, relying on a single workspace for everything is a recipe for disaster. The basics of robust architecture dictate that we divide our lifecycle into at least 3 environments: development, staging, and production. Why? Primarily for security and stability. You absolutely do not want experimental code inadvertently breaking a live model that customers are actively using. Furthermore, separating workspaces protects sensitive data. Developers can work with anonymized data in the dev workspace without ever having access to the real, highly secure data residing in the production workspace. How do we achieve this? We provision a distinct Azure Machine Learning workspace for each phase. As we deep dive into this setup, we align these workspaces with our source control, like GitHub. A feature branch might deploy to the dev workspace, while merging a pull request into the main branch triggers a deployment to the staging workspace for automated quality assurance checks. Looking at this flowchart, you can easily perceive the logical progression of our machine learning assets through the different workspaces. On the far left, we start with the development workspace. This is the sandbox. It is where your data scientists spend their time experimenting, running training scripts, and tracking their initial runs. Once a model reaches a certain performance threshold, it doesn't just jump to the live app. Instead, it flows into the middle node, the staging workspace. This acts as our safety buffer. Here, automated testing, linting, and QA processes take place. We might even deploy a test endpoint to ensure the model responds correctly to API calls. Only after passing these rigorous checks does the model finally advance to the production workspace on the right. This production node is locked down, highly monitored, and serves the live predictions to end users. This visual perfectly encapsulates the outer loop of MLOps, ensuring that every transition is deliberate, tested, and secure. Moving on to the how do we actually set up and secure these workspaces for automation? The definition of a secure setup involves establishing robust authentication, so our CI/CD pipelines can interact with the Azure Machine Learning workspace without human intervention. The basics here rely on Microsoft Entra ID, formerly Azure Active Directory, and a concept called service principals. Why do we use service principals? Because when an automated GitHub action needs to trigger a training job, it cannot pause and ask for a password. It needs a secure, non-interactive way to prove its identity. How is this done? First, an IT administrator creates the service principal using the Azure CLI. Then, we take the credentials for that service principal and store them securely as a secret within our GitHub repository. For a deep dive, it's crucial to understand that we don't just give this identity blanket access. We use Azure's Role-Based Access Control, or RBC, to assign the principal of least privilege. This means the automation identity can only perform actions within the specific workspace it is assigned to, keeping our cloud environment highly secure. Let's break down this security architecture using the diagram on the screen. At the top, we start with the GitHub repository, which houses your machine learning code. When a developer pushes a change, it triggers the next node, GitHub Actions. Now, GitHub Actions needs to talk to Azure, but it encounters a locked door. This is where the diamond-shaped node, the service principal, comes into play. GitHub Actions uses the securely stored credentials to assume the identity of the service principal. Think of the service principal as an automated VIP badge. Once authenticated, the arrow points down to the final destination, the Azure Machine Learning Workspace. Because the service principal has been granted specific RBC permissions, the workspace accepts the connection and allows the GitHub action to start spinning up compute clusters, registering models, or deploying endpoints. This flow ensures that every automated action is authenticated, authorized, and fully auditable. Let's take a deep dive into the development workspace, which facilitates what we call the inner loop of machine learning. What is the inner loop? It is the highly iterative, experimental phase where data scientists try to find the optimal model. The basics involve taking raw data, pre-processing it, configuring features, and training various algorithms. Why do we isolate this? Because finding the best model involves a lot of trial and error, which consumes compute resources and generates massive amounts of metadata. You need a dedicated sandbox for this. How do we execute this? Within the workspace, data scientists use managed Jupyter notebooks or automated ML. Automated ML is fantastic because it runs multiple training jobs in parallel, testing different algorithms automatically. Going deeper, to make sense of all these experiments, we utilize MFlow. By enabling MFlow autologging in our training scripts, the workspace automatically records every hyperparameter, every metric, and every model artifact. You don't have to manually write log statements. The workspace becomes a searchable, highly organized database. This flowchart beautifully illustrates the inner loop journey inside the development workspace. Starting at the top left, we have our raw data. This data flows into the Jupyter Notebooks node, representing the interactive environment where data scientists write their Python code. From there, the process moves into the model training phase. Notice how the training node feeds directly into MFlow autologging. This is a critical junction. As the model trains, MFlow acts like a silent observer, capturing the accuracy, the loss rates, and the specific configurations used. Finally, the arrow leads to the workspace registry database at the bottom. Once the best model is identified perhaps through an AutoML sweep, the final artifact is securely saved in the registry. By visualizing it this way, you can see that the development workspace is not just running code. It is a meticulously structured pipeline that guarantees no experimental insight is ever lost, bridging the gap between raw data and a trackable model asset. Now we transition to the outer loop, focusing on our staging and production workspaces. What exactly is the outer loop? It is the operational phase where a finalized model is packaged, tested, and deployed for consumption. The basics involve taking that registered model from our development phase and wrapping it in an API. Why is this two-step staging and production process critical? Because an AI model making real-world decisions must be completely reliable. Staging allows us to catch errors before the users do. How is this orchestrated? We use the Azure Machine Learning CLI version 2 combined with GitHub Actions to automate the creation of managed online endpoints. When does this happen? The deployment to staging is triggered the moment a data scientist merges their feature branch into the main branch. Deep diving into this, we implement a human-in-the-loop approval gate. The model sits in the staging workspace, undergoing unit tests and integration tests. Only when a senior engineer reviews the test logs and clicks approve does the pipeline proceed to push the model into the live production workspace. Trace the path on this diagram to understand the outer loop deployment strategy. We begin on the left with our registered model. The first transition takes it into the staging workspace block. Inside staging, the model is pushed to a test endpoint. Here, automated scripts bombard the endpoint with dummy data to ensure it returns predictions quickly and accurately, without crashing. Following the test endpoint, you'll see a distinct diamond shape representing the approval gate. This is our manual failsafe. The automation halts here, waiting for a human to verify the staging results. Once the green light is given, the flow crosses over into the production workspace. Finally, the model is deployed to the real-time endpoint, which is the live, public-facing API. This diagram highlights that while we heavily leverage automation for efficiency, we maintain strict architectural boundaries and human oversight to guarantee that only the highest quality, fully verified models ever make it to the production environment. To make our multi-workspace architecture function seamlessly, we need to properly manage our deployment environments. What does this mean? It means explicitly linking our GitHub repositories environments to our distinct Azure machine learning workspaces. The basics involve navigating to your GitHub repository settings and creating logical environments named development, staging, and production. Why go through this extra administrative step to eliminate human error? You want to make it technologically impossible for a test script to deploy an experimental model into your live production workspace. How do we enforce this? We use environment secrets. Instead of having one global secret, we store the development service principal credentials strictly inside the GitHub development environment and the production credentials inside the production environment. For a deep dive, this allows us to enforce strict branch protection rules. We configure GitHub so that only code merged into the main branch is permitted to access the production environment secret, thereby tightly locking down access to the production Azure workspace. This diagram maps out the secure relationship between GitHub and Azure. Starting at the top, we have the overall GitHub environment's configuration. This splits into the environment secrets management layer. Notice how the path diverges here. The repository holds a distinct dev secret and a distinct prod secret. The arrows clearly show the isolation. The dev secret only has the authorization to communicate with the dev workspace on the bottom left. Conversely, the prod secret is exclusively mapped to the prod workspace on the bottom right. There is no cross-contamination. If a GitHub action running on a feature branch attempts to push to production, it will fail because it cannot access the prod secret. This visual perfectly demonstrates the principle of least privilege in action. By structurally isolating the credentials at the source control level, we guarantee that our Azure machine learning workspaces remain completely segregated, preserving the integrity of our production machine learning applications. Let's pivot back to an advanced capability within your workspace, hyperparameter tuning via sweep jobs. What are hyperparameters? They are the configuration settings for your algorithm, like learning rate or batch size, that dictate how the model learns. The basics involve defining a search space A range of possible values for these settings. Why do we use sweep jobs? Because manually guessing and testing these values is incredibly inefficient. A sweep job automates this by spinning up multiple training runs with different combinations. How is this executed in the workspace? You define a base command job with your training script, and then wrap it in a sweep configuration using the Python SDK or YAML. Deep diving into cost optimization, we don't just run every combination blindly. We use advanced techniques like Bayesian sampling, which uses previous results to pick smarter hyperparameter values for the next run. Furthermore, we apply early termination policies. If a specific training run is performing poorly compared to others, the workspace automatically kills that job, saving you significant compute costs and time. Follow this flow to see how a sweep job operates within the workspace. We start at the top with the developer push, representing the engineer submitting the YAML configuration to Azure. This triggers the GitHub action, which constructs the base command job. This base job contains the core Python training script. However, the real magic happens at the next node, the sweep job configuration. Here, the workspace takes the base job and fans it out, creating multiple parallel trials. Imagine the diagram expanding into multiple concurrent training runs, each testing a different hyperparameter, like learning rate 0.01 versus 0.1. The workspace actively monitors all these parallel runs. Thanks to early termination policies, failing runs are cut short. Finally, the various paths converge at the bottom node, the best model output. The workspace automatically evaluates the logged metrics like highest accuracy, selects the ultimate winner from the sweep, and registers that optimized model for you, completely automating the tuning process. Let's bring this all together with a real-world use case that perfectly illustrates why managing workspaces is so vital. Imagine you are a machine learning engineer at Prosware, a healthcare startup developing an app to predict diabetes in patients. Because you are dealing with highly sensitive medical data, security and isolation are your top priorities. You implement an MLOps strategy utilizing three distinct workspaces. First, the development workspace. Here, data scientists experiment freely using anonymized data. They have no access to actual patient records. Once a model shows promise, the code is pushed to a GitHub repository, triggering an automated GitHub action. This action packages the model and moves it to the staging workspace. In staging, the model undergoes rigorous automated testing and linting, ensuring it meets quality standards before deployment. Finally, after manual approval from a lead engineer, the model is pushed to the production workspace. This production environment is locked down, containing the real-time endpoint that the practitioner's web app calls to get live predictions. By strictly isolating these workspaces, Prozware guarantees privacy and safe innovation. This final diagram paints the complete picture of our Prozware healthcare scenario. On the right, we have the ultimate goal, the Prozware app communicating with a real-time endpoint inside the locked-down production workspace. Note the label patient data. This sensitive data stays strictly within the production boundary. Now look to the left. We have our data scientists. They interact exclusively with the development workspace, utilizing only safe, anonymized data for their experiments. When they finalize a diabetes prediction model, the flow moves along the bottom path via GitHub CI/CD automation. The model is seamlessly transported into the staging workspace. Here, it undergoes rigorous simulated testing. Once it passes, an engineer provides the manual approval, allowing the model to bridge the gap into the production workspace. This architecture solves the business problem perfectly. It allows data scientists to innovate rapidly in a secure sandbox, while shielding the live healthcare application and patient data behind multiple layers of automated testing and strict workspace isolation.